Okay, it's great to resume the CS Colloquium after many months. It's great to have Pranjal Datta give a talk. He's currently a postdoc at the School of Computing. His broad research area is complexity theory. He finished his PhD in computer science in 2022 from Chennai Mathematical Institute under the guidance of Professor Nitin Saxena. He's the winner of the ACM India Doctoral Dissertation Award 2023, and this is what we are here to celebrate. And during his PhD, he was a recipient of the Google PhD Fellowship from 2018 to 2022. He obtained his bachelor's in mathematics and computer science and master's in computer science, both from Chennai Mathematical Institute. So all through CMI.
Okay, yeah. Oh, thanks, Divesh, for giving me an opportunity to give the talk. So this talk is basically a very, so I have tried to assemble a very few topics from my thesis, and I'll try to present informally, or I'll try to be non-technical most of the time so that people understand the significance of the problems that I have tried to tackle, rather than getting into the nitty-gritties of the technicalities. So let's start. So yeah, so the point is, this is a conversation between two chickens, and then the dad trying to say that, well, whether it has some value or not. I'll try to convince that it is not obscure. This has some scientific value, hopefully at the end of the talk. If not, please let me know. I'll try to change my slides. Okay. So uh, so there will be 4 different topics in some sense, and I'll try to connect these 4 different topics. So first question is very basic questions in algebra, that if I have a univariate polynomial f of degree d, how many roots can it have? Right? How many zeros can it have? And we know that it can have at most d many roots. This follows from fundamental theorem of algebra. If we are over rationals or so on, and over a finite field, it has at most d many roots, not complex, but d many roots. But the question is, does the number suddenly get better when we are talking about real roots? By real roots, I mean the roots which are real numbers, right?
What do you mean by better here?
Better meaning, can it happen that it has better dependence on d, right? Or some other parameter than degree?
So you are happier with fewer roots?
Yeah, I am happier with fewer roots. Okay. Yes. So for example, maybe
no, just when
yeah, this will actually come. This will come. Yeah. So for example, but when you are saying exactly the question, when you are saying better with respect to what? Because of course we can take d many real roots and multiply, like product x minus 1 times x minus 2 dot x minus d. This has d many roots and so on. So we cannot do better. But the question is, can we do better in terms of sparsity? Let's say sparsity means number of terms. Of course, degree d meaning this has d many terms or d plus 1 many terms, right? But the sparsity can be very small regarding, let's say it has degree d, let's say x to the d minus 1. It has degree d, but only 2 terms. So sparsity is 2, right? So in those cases, can we do something better than that, right?
When you say term, you mean, okay, it's like this.
Yeah, I mean, no, so if you expand this, this is like your x to the 9 plus x minus x to the 8 minus 1, 4 terms. Like terms meaning like how many monomers, like it, so these are four terms, degree is 9. So in this case, the question is, can we say something better? Like, does it have smaller roots, or can you say what is the number of roots? And you can say that for this case, it has only one real root, x equal to 1. It cannot have other real roots because x to the 8 plus 1 cannot be 0 when for any real number, right? So it has only one real root. Now, if you know Descartes' rule, let me remind what Descartes' rule says. It's a very interesting rule. It says that if I have a so it take an invariant polynomial, the number of sign changes in the coefficient. So there is, let's say, x to the 10 minus 9 x to the 9 plus 8 x to the 8. So the number of changes plus minus is happening. That actually is an upper bound on the number of positive real roots. Is it clear what Descartes' rule says? The number of sign changes in the coefficient, if you look at 1 by 1, then it is the upper bound on the number of positive real roots.
the number of sign change.
It's a number of sign changes. So if it is all plus, let's say, like, then it basically is saying it cannot have, well, I mean,
Is it not exactly that?
it can be even, there are typical examples where you can come up with some weird examples, but yeah, most of the, yeah. So the sign changes is basically the number of positive real roots, okay? So now, if it has s many terms, it can have at most s minus 1 many changes. At most, let's say everything is alternating, then it has s minus 1 many changes. So then it can have at most s minus 1 positive real roots. And the same thing game you can play, and so that it has also had s minus 1 negative real roots as well. So Descartes' rule will say that this polynomial can have 2 times s minus 1 many real roots, non-zero real roots. It does not talk about zero. I mean, you can, x equal to 0, you can forget about it. That, I mean, otherwise, these are all non-zero real roots. Okay. And note that this sparsity can be, as I said, significantly better than degree. Okay. So the question is, does it hold for integer roots? When we are talking about integers, can we do even better in some sense? Because integer is real, but real might not be an integer, right? What about random polynomials? If I give you a random polynomial, what can you tell about its roots? And the main point is, what is the connection to computer science or computer theory? Why are we even interested in this question? So I'll talk about the random polynomial case, and then the whole talk will be to connect to 3 different topics in complexity theory with this question. That is the talk. Okay. So it turns out it's a 8 years old result. It turns out that when f is random and dense in the sense that every monomial is there. So x to the d is there, x to the d minus 1, x to the d minus 2, every coefficient is there, but these coefficients are, let's say, random. You are sort of picking it randomly. It turns out that the number of real roots is really small, like log d.
What do you mean random?
So what you can say is that you fix a set S, finite set S, and you are looking at, and then you are taking the limit. If one of the definition is probably this, there could be other definitions as well. Like you pick up S, set S, fix a set S, which is finite, and then you are picking the coefficients independent from that, and then you are taking the limit. I mean, yeah.
The limit will still be countable, right?
Yeah, of course, yeah. But then they'll say this is degree, this I'm talking about degree. So there is no sparsity because the degree can be large, sparsity can be small. So let's say you have a random A sparse polynomial. That means, let's say I have many so very small monomials, but it is sort of like scattered. Like the degree is really large, but there are like very few monomials, like S many monomials. What can you say about S many terms? What can you say about that? It turns out that you can show it's like square root S independent of D. So no matter how how large the degree is, it only depends on the number of terms of F. So random F can have small number of real roots. That's what the question is. Oh, that's what the result is. Now, one small observation is that if F and G, 2 polynomials, where f and g has sparsity s, that means it has they have s many terms, then if g has order s many non-zero real roots. Why? Because f has not, as I said, Descartes' rule says that f has order s many real roots, g has order s many real roots. So f times g also has order s many real roots, because any real root of f times g must be real root of f or a real root of g, right? So that's why the number of real roots of fg is also order s. However, sparsity of fg can be s square, because what you are saying is you are multiplying s many terms with another s many terms. So worst case, every monomial terms can survive. So there are s square many terms. So the sparsity can be really large, but the number of roots is small. The question becomes, what happens if you just add 1? What can you tell about this polynomial 1 plus fg? Note that again 1 plus fg has s square or s square plus 1 sparsity terms. But what can you tell about the number of real roots? Is the question clear? That I have 2 polynomials, sparse polynomials, like number of terms s. You are multiplying f times z and adding 1. What can you say about the number of real roots?
Here you want to say order square root s, right? Not order s.
No. So if it is random, then yes. If it is arbitrary, then Descartes rule. You use Descartes rule. Like if it has s many, then s terms, then if f has order s many, like 2 times s n minus 1, and g has 2 times s minus 1, so whatever, 4 s many. And for this, nothing better than sparsity bound is. Like fg has sparsity s square, and nothing better than s square is. Okay. And this sort of is the, or was one of the motivation for me to start understanding this model and connect to complexity theory, because so this will be basically the talk that like what do you mean by generalization, what do you mean by model of computation, and what are the implications. That are the main things. These are the main things.
Sorry.
Yeah.
What went wrong when you passed the one?
Oh, because if let's say if alpha is a root of a for g, then you cannot say that, right? I mean, alpha is a root of 1 plus, because this is 1 plus. But when there is no 1 plus, then I mean, if alpha is 0, and I mean, yeah.
Roots carried forward.
Yeah.
FG has the roots of f plus the roots of g, right?
Yeah.
But 1 plus fg does not have that property, right? So that's the problem with 1 plus fg.
But why?
Oh, it will be clear. I mean, so their question was 1 plus fg because of some Newton polygon and some math result. I mean, that will, but there are other direct implications of that 1 plus fg looking at that. But that's what I'll try to say. I mean, in some sense, I'll try to say that 1 plus fg, or maybe not 1 plus fg, somewhat studying this 1 plus fg would actually solve a lot of problems. So it is a hard question. It is not easy to solve. It will be the message.
So basically your idea is that you want to change FG slightly without changing the sparsity, but now.
Yes, and but then you would want to say that if you do this, then a lot of things are happening. Yeah, that is that. So now, as I said, that the connection will be to talk about 3 themes in algebraic complexity, these 3 different topics, and that will be sort of the basis of the talk. That so I'll talk about these 3 problems, and these are the 3 problems. One is the matrix rigidity, or it is nowadays also called Netflix problem, which is the I'll talk about this problem a bit. There is a problem, and there is this algebraic p not equal to np, which is the vp not equal to vnp, and then there is this question of de-randomization. I'll talk about all the themes. I mean, there is nothing. I mean, this, if you don't know the terms, that's completely okay. I'll just
Definitely did not know about.
yes. Yeah. No, actually, I saw that even apparently there is a Wikipedia page saying Netflix problem. I'm like, wow. I mean, I saw in some lectures, and then I said, wow. I mean, so okay. So the talk is, can we unify, or can we come up with a one single problem that if we solve that, we will solve all these 3 problems, right? And the point is, or the major portion of my talk will be this. Yes, we can do, which is called the tau conjecture, which is basically studying the real roots of a polynomial. That is basically the thing. So let's go over one by one of the 3 problems. I think matrix rigidity is one of my most favorite problems. So let's start with matrix rigidity. I don't know how many of you know, but let's go over it. So it's a very basic question. So I have a matrix A that is given, and I also have some number R that is given. What I want to do is I want to change the entries of A so that the rank becomes less than or equal to R. How many? So the question is, how many entries do you have to change to make it less than or equal to R? That's the rigidity of a matrix A for the rank. Okay, is the definition clear? I have a matrix A. I want to change a few entries here and there to anything, and then I want to know that how many terms do I have to change so that the rank becomes less than or equal to R. You can also think it a bit pictorially. So let's say A is the matrix, and this cross here are your target things. Let's say I want to change these S places. So this S places is basically the C. C is basically the sparsity, meaning the number of entries in C. C is S, and then suddenly when you are adding A plus C, meaning you are changing all those S places, suddenly the rank becomes less than or equal to R. Pictorially, this is what you are trying to say.
You start with
A.
rank R.
Sorry?
Your starting rank is R.
No. I'm saying rigidity of matrix A for rank R, not of rank R.
For rank R.
So it's like so I am giving A and I will say that rigidity for rank R is the number of changes such that the rank becomes less than or equal to R. Yeah. So of course, if the rank of A is already less than equal to R given, then I don't need to change. I mean, then this is already an less than equal to R. But the question is, it can be full rank matrix, right? I mean, then what can we do? And it usually denoted by RA or R. I mean, field you can all in this topic can also probably ignore, but this is the rigidity of matrix is this. Like for A, you want to achieve R, how many changes you require. And it also captures in some sense the Hamming distance between a matrix and the less than equal to R rank matrices in some sense, right? I mean, how many changes you need to do. Okay. So this is definition clear? Yeah. I'll come. The next slide is about that. Yes, I mean it looks very cute, but suddenly I mean it is extremely hard. Okay. Okay. So first of all, let's just talk about identity matrix. Suppose you have an identity matrix n cross n. Yeah.
Why is it called Netflix problem?
Yeah, I will. Yeah, I'll get there. So for the n cross n identity matrix, you can see that you can change n minus r many entries. Like all the ones you can basically change this to 0 in the, let's say, diagonal, like lower diagonal, and then you get a n minus r, and you can show that this you have to change this many. Now, for any matrix A, you can show that this is less than equal to n minus r square. Okay, and the way to look, think about it is you have a matrix. You want, so let's say it has rank R. I mean, it has more than rank R. So take a R cross n matrix, which is the full rank matrix, and then the complement n minus R cross n minus R. You can actually change it. You can show that there is a way to change n minus R cross n minus 1 matrix, the complement matrices, such that the rank will become less than equal to the rank will become exactly R, the top. You can show that. Okay. There is a way to do that. Okay. So it is less than equal to n minus r square.
But you're saying that always true.
Yeah,
Okay.
less than equal to n minus r square.
Pick a linear dependence, right? And you can basically adjust this bottom.
Yes.
No, but you're keeping only one quarter, right?
So I have R cross R matrix. This is full rank. You take n minus R cross n minus R.
Yeah.
You can think of them as in fact a variable, and you are trying to understand what values to put so that this becomes this.
You're changing, not removing.
Yeah.
Okay. Sorry.
It's not just zero. Yeah.
I was zero.
No, yeah. Yeah, 0 might not lead to smaller. Yeah, you have to change it. And it is actually equal to n minus r square for a random matrix. You can show that for a random matrix, you have to change n minus r square many things. So that is the optimal way that I just described. But we want to understand explicit. So we want to come up with explicit rigid matrices in the sense that we want to come up with matrices A which has large rigidity, meaning you have to change lot of entries to make it less than equal to R. And there are some results like where some explicit matrices where you have to change like n square by R many entries. Now coming back to this question of hardness. So given a matrix, deciding whether this rigidity is less than equal to S or not, that means whether you have to given a matrix A, rank R, and S many, the parameter S, can I change S many terms so that the rank becomes less than equal to S is hard. Over finite field, it is NP complete. Over real, it is in P space. And over rationals, it is not even known to be decidable. Okay, this is extremely hard question. And what is the Netflix problem? This slide variant of this rigidity, where initially we were given A and you have to change, right? And here some of the entries of A are given, but it is incomplete. You have to put values in the other entries, which is not given, such that the rank becomes minimum. Or the rank becomes less than equal to. That is the netlist. And you can think of this as, let's say you have what is the ijth entry? Let's say ith user has seen or watched the jth movie. Let's say you have a lot of users, a lot of movies. Ijth entry is ith user has watched jth movie and has given some rating. So that is that. And if it has not, then you don't know. You want to minimize the rank because you want to understand very few properties and try to predict what is happening, like what kind of movies a user will like. So this is where this Netflix problem comes. Okay.
Why is there linearity in this process?
No, so they basically this rank what they do what yeah, that is of course I mean
You assume.
assume.
You assume that it's linear.
The linearity is, let's say you have watched some movie, I have watched some movie, right?
Okay.
Prashant may be a point between us. Like you was 20% like
Well, that's combination.
yeah, 80% like you, 20% like me, that's right. That's the underlying structure.
Actually. Okay.
Okay. So this is one theme, which is the matrix rigidity. Okay. Let's go to some of the implications. It is known that this rigidity implies some important lower bound on computation complexity. This is a famous result by Razborov back in 89. What he showed is that if you can show rigidity lower bound, then there are computable functions, explicit computable functions, for which the communication complexity is really large. There are some lower bound on the data structure. This is by Dweir and Shasha and Winston. Dweir also
Like in practice, they actually solve the Netflix.
yeah.
Right?
Yeah.
So what's
No. So Netflix problem I'll again come. So this is exactly not matrix rigidity, as I said, because there is a slight difference between matrix rigidity and matrix completion or the Netflix problem. Matrix rigidity says you are allowed to change any s many things, right? It's not here. The initial matrix is fixed and other things are unknown. So it is much more like finding the values where I mean, it is
it's a planted version.
yeah, it's and this actually reduces something called the polynomial identity testing that I have already said. So that is actually solvable almost in very fast. So there is connection between rigidity and locally decodable code or self-correctable code. And this is just a very few point. I mean, if you can show some lower bound, then this also implies some lower bound on linear circuits. And this is one of the most important questions for 45 years that is open, that can you show that there are matrices where you have to change more than superlinear many n, such that the rank becomes epsilon times n. And if you can show that, then there are lower bounds known in the linear circuits. So what is a circuit and so on and so forth? I'm just coming in the next thing. But the point is rigidity is a very important problem and we would like to understand it better. And one thing I would also like to say that last 10 years, there have been many research on rigidity matrix coming up, trying to prove rigidity. And most of the proofs are actually negative results. People thought this is many matrices are rigid, but what turns out that they are not rigid. Like yeah, there are, I mean, for example, circular matrix, DF, like the DFT matrix and so on and so forth. Like there have been all these results where say that people thought these are rigid, but turns out they are not rigid. So still a good candidate is when like R of, let's say, for example, this case, like you have to change into the 1 plus delta many terms, like superlinear many things so let's say you have so that the rank becomes, let's say, epsilon times, let's say n by 100.
And these are square matrices?
Yeah, square matrices. Yeah. Okay. So this is
We don't know even with like tiny delta.
no. Like no. Even delta is 0.001, we don't know. Yeah, what we don't know is that this delta is so, what we know is n times polylog n type of things. That is not good enough. Okay. All these examples that I was saying, it was not rigid because of n times polylog n, but not, yeah.
So right now people have examples of lots of different
Non-rigid matrices.
non-rigid.
Rigid matrices,
Not-
yeah.
They're not able to find related.
Yeah, I mean, there are candidates, but people started saying that, oh no, this is, you thought this is rigid, but this is not. Oh, you thought this is rigid, this is not. Rigid in the sense that, well, I mean, in this sense, but yeah. But of course, you know that random polynomial, random matrices are rigid, so if you, it has to stay there. I mean, but it's just that you have to find it. Okay, so this is the second theme that I want to talk about, which is the VPBNP or the lower bound question. And here the model is slightly different. It is a circuit, algebraic circuit. What is an algebraic circuit? You have variables at the bottom, and then you have plus and products in the gate, and you are computing a polynomial in the most obvious way. And there is no, and for example, this product, this is a plus gate, so this is computing x1 plus x2, and there is a force, so this is computing 4x1 plus x2, and this is plus, and then similarly you are computing a product here, and then eventually plus here, and it eventually computes a polynomial in a more syntactic way. This is the representation. And the size basically is the measure here. And the size is basically you can think of this as the graph, data graph from bottom to top, and then the size is the measure actually is the size of the graph, which is the number of nodes and edges. Okay, this is like just like Boolean circuit, but instead of and or, you are just taking plus and product. And size of a polynomial is the minimum size circuit computing it, because there could be many circuits computing the same polynomial, right? And you want to understand the minimum circuit, minimum size circuit that is computing this. Okay, so this is clear, I hope. And so this is the depth. The depth is basically from the bottom to top. This is the depth 3 because 1, 2, 3. That's fine. Okay, so what is the size? So size can also be thought of as the number of additions and multiplications you need to compute f. Because the circuit is exactly doing that, right? I mean, there are plus and multiplication, you are computing f. So size of f is the minimum circuit, meaning the minimum number of additions and multiplications to compute f. And also, if I have a circuit, I can evaluate a point at a point easily, because if I want to understand the f of a, I basically give the points. This is some plus is happening, some product is happening. I can just do one by one. So evaluation is very easy given a circuit, right? So now these are two examples where I would say that these are easy polynomials. What do you mean by easy polynomials? I have defined a model which is computing. I would say it is easy if it can be computed by a polynomial size circuits, right? And by polynomial size, for example, x1 to the n plus dot 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 xn to the n. You can trivially compute because x1 to the n you can just multiply n many times, or in fact log n many times, like x1 and then you can repeat it square. So this has very small size circuit. The second example is important because although it can have exponential many term monomials, like 2 to the n, right? All possible monomials is there, but there is a syntactic way of expressing it, which is product 1 plus xi. And this has a small circuit because there's product and then 1 plus xi. So these are all easy polynomials. Okay. The question is, are all polynomials easy? Can you always compute polynomials via small size circuits? And it turns out that if you allow your degree to be exponential, then of course there are hard polynomials. I mean, you cannot compute all the exponentially hard, degree polynomials by a small size circuit. Point is, a circuit can compute a exponential degree polynomial. Why? Because a repeated square, let's say x, you compute x square, and then again x to the 4, x to the so on, and so x to the 2 to the n can be computed. So exponential degree can be computed, but you can show that exponential degree polynomials, there are exponential degree polynomials which are not easy, cannot compute. But of course, we are not interested in this regime. I mean, of course, we want to understand polynomial degree regime. So the question is, are there hard polynomials? That means, are there polynomials which has degree poly-n and it cannot be computed by a polynomial poly-n size circuit? That means the size is super polynomial in N. Are there such hard polynomials? Right?
So the number of terms is not fixed.
Number of terms is not fixed. Like Fn is like, yeah, nothing is, it can have degree n, I mean degree poly n or something, and then you want to understand the, so degree n, let's say when degree n can have what, n plus n choose n many terms, like whatever, like exponentially many, because n variates, n variables, and then n terms, right? So this can have like lots of monomers, right? But as I give the example, right, this sum of product of all xi, I mean this example where it could have like 2 to the n, all monomers are there, but still it has small size circuit. So you cannot, yeah, succinct, it can happen. So you cannot just say that, oh, look, there are a lot of monomers, that's why this is hard. That you cannot say. Yeah. But it turns out that random 0, 1 coefficient polynomial is hard. That means, as you are saying, that let's look all the coefficients, look at all the monomers, and you are picking up the coefficients, either picking or not picking randomly, and then you can show that there is no polynomial size circuit computing that. It is hard, basically. If there is, it cannot be computed. In fact, you can show that to compute this is require an exponential size circuit, not even super poly. Like you really have to. So basically, monomial by monomial is sort of the only way of computing that. It is sort of saying. So trivial way of computing is monomial by monomial. That is a hard polynomial. But
It's like SAT.
it's some sense, yes,
SAT and
yes,
stuff.
yeah, exactly, yeah, exactly, yes, yeah. So one candidate hard polynomial is the path polynomial, n by 2 length path polynomial. What is this? So suppose I want to understand number of n by 2 length path in a graph G. Okay. If I evaluate this polynomial path on the graph G, by evaluating I mean xi comma j is 1 when there is an edge between I and j vertices, otherwise 0. You see, this is exactly what all the n by 2 length path computes, because this has to compute all the n by 2 length paths, because we are summing over all possible I1 up to IN by 2 plus 1, right? So as I said, path on an n-vertex graph G computes the number of paths of length n by 2, and this is of course hard. I mean, this is NP. This is how P complete, but yeah, this is NP. I mean, so similarly, we can think of Valiant's conjecture, which is the VP not equal to N. It says that there is no way there is a small circuit that computes this polynomial. These are whatever n by 2 plus 1 degree polynomial, right? N by 2 plus 1 degree polynomial on whatever n square variates in n variables. And the conjecture is that there is no way there is a small size circuit. You can think of this as follows, at least intuitively. If there was a small size circuit that was computing this, then you can evaluate, because then you can put 0 and 1 and you suddenly get the number of paths, right? There are some subtleties that I'm not saying, but so intuitively this should be hard. The circuit, I mean, this should be super polynomial large, which is called the VP not equal to NP, which is the algebraic P not equal to NP. So is this setup clear? So you have a circuit and you want to understand hard polynomials. Like there are hard polynomials that cannot be computed by this, and this is one candidate polynomial. Valiant, yeah. Okay.
So sorry, computing the number of paths of length n by 2.
Is basically, so if you have a graph G, what you want to understand is basically evaluate at xij equal to whatever that, right? I mean, if you could evaluate it, then you will get that.
You get the total number of
Total number. Now, suppose I'm saying that suppose there is a circuit that is computing that. Eventually, you are saying, okay, I have a circuit. I now put xij equal to 1 and 0 accordingly at the leaves. And then it's a small size circuit. So subsequently, it will compute something, right? But the catch is that, but this is not so, I mean, but it is not clear that this implies this is hard, because the point is in the circuit, you are allowed to use arbitrary constants like 2 to the n or something like that. So maybe there is a small size circuit, but then maybe you are using arbitrary constants there. So it does not help in that sense. In that sense.
And it sounds like computing the number of paths of n by 2 is hard.
Yeah, NP hard. Yeah, I mean, it's sharply complete. Yeah.
It's not okay.
It is a hard problem in the Boolean, and we were trying to mimic it in the algebraic world, yeah, circuit sense. And yeah, why are people interested in this? It turns out that it is sort of squeezed in between two questions. The non-uniform P not equal to NP question implies VP not equal to NP, and VP not equal to NP implies P not equal to NP over a what something called BSS model of computation, a plum sub smell computation, where they thought Turing machine over complex numbers like arbitrary addition and multiplication you can do, and there you can also do define P not equal to NP. And it turns out that these are this is sandwiched between those two things. And of course, VP equal to VNP also implies polynomial hierarchy collapses. So people don't expect this to happen. So, so hopefully VP not equal to VNP. Right? Okay. So so this is the connection. So you want to understand VP not equal to VNP. This is the second thing. So there are two themes I have covered: polynomial identity testing, matrix rigidity, and valence conjecture. Then there's the third thing, which is a completely different topic, seems to be. Suppose I am given a circuit, see, what access do I have? I can query it. Like, give me the value at 1, 1, 1, 1, 1. Give me a value at 2, 3, some value, and it will just output me. Now, can you check whether the polynomial, eventually the polynomial that is being computed, this is 0 or not? Who knows? I mean, it is a circuit, right? So who knows? There could be cancellations going on, right? Even if it is a circuit, there could be cancellations going on. So you don't know whether this is 0 or not. You want to check deterministically with this 0 or not. Now there is this lemma called polynomial identity lemma. This is proved by many people over many years. And so this basically says that if P is indeed a non-zero polynomial, then if you evaluate it at a random point, it must be non-zero. That's what the lemma says. Okay. So using this lemma, one can understand this PIT actually has a randomized polynomial time algorithm, because you are given a circuit, you basically evaluate at a random point, it must be non-zero. If it was indeed non-zero, otherwise you. So randomized polynomial time. The question is, so but P equal to BPP is an open question. That means whether every randomized polynomial time algorithm can be randomized or not. Whether every algorithm which has a randomized algorithm, can we remove the randomness? Can we show that there is a deterministic polynomial time algorithm for that? Is an open question. And this is one very important question that is remaining, that whether we can show that PIT can be randomized or not. Now, what turns out that valence conjecture implies PIT has a sub-exponential time algorithm. Okay. This is called the hardness versus randomness sort of trade-off. Like if you can prove something is hard, suddenly you can turn it into a better algorithm. Then suddenly you have a better PIT. Okay. So for now, PIT is an exponential, like deterministical, because you have to try all the things. Randomization, it is in polynomial time. Without randomization, we don't know better than exponential time. But if you can prove that there are hard polynomials, then suddenly you can use it to do use it in the algorithm and remove randomness. This has been going on for some time in the Boolean world as well. This is called hardness versus randomness. Whenever I have some hardness thing, then I can turn it and use it in some other problem and come up with a better algorithm.
How?
Oh.
Means kind of what? Hardness of this thing implies a solution or a derandomized solution to PIT.
Yes.
How? Okay, there's some complicated.
It is.
Not worth the time, right?
Yeah, but I can tell you offline maybe, but yeah, it is so yeah, so this is a remarkable result. And not only that, what it turns out is that if you can show that the path polynomial that I showed, it requires exponential size circuit, which is probably expected, right? I mean that it requires exponential size. Then actually PIT has a quasi-polynomial time algorithm. Okay, it has a quasi-polynomial time algorithm. However, the opposite direction is not. Suppose I can do good PIT. I have an algorithm. Can you turn it into a hard polynomial? Nobody knows how to do it. Okay. So this is the PIT question. There are a lot of applications. Let me quickly. Yeah, there are a lot of applications of PIT. For example, the best matching parallel algorithm for perfect matching, that is actually via PIT, like de-randomizing a special case of PIT. This second point, which is the primarity testing, primes in P, that was also a special case of PIT. It turns out that this Mulmule-Vazirani had this very famous isolation lemma back in 1987. it turns out that if you can de-randomize isolation lemma, you actually de-randomize PIT. Okay. The question of matrix completion, that how to find the other values, it is actually, you can think of these as variables and finding values so that this becomes 0, something like that. Determinant becomes 0. And then suddenly it is a PIT question. And that has a randomized algorithm. So that's what usually what they use. That for the most of the cases, we know how to solve it.
The Mulmula was done what was it for?
Isolation lemma for matching. So basically, so let's say you have a lot of matchings. You want to understand, find. So then there is a problem. What it says is that you can sort of give weights, and if you put weights randomly to vertices, then there will be a unique minimal matching in some sense. That is the same thing for 3-SAT to unique SAT kind of reduction. Like you have a 3-SAT, there are a lot of solutions, but if you put weight, suddenly there is a unique SAT. Like there is one solution in some sense. So this kind of reduction, that's what isolation lemma does, and suddenly this also has application in PIT. And factoring is equivalent to de-randomizing PIT. I mean, suppose I'm giving you a polynomial and I want to understand the factors of it. And suddenly if you want to, and there is a randomized algorithm to give a deterministic algorithm, that suddenly this is by, this factoring result is by Koperty, Saraf and Spilka 10 years back. And this is a small advertisement of which I'm writing a survey. So hopefully there you'll get some good intuition, and this will be informal. So you can look into more applications and more recent advancements. Okay. So a quick recap. We have defined 3 themes: matrixity, VP-BNP, polynomial PIT. Matrixity to VP not equal to VNP is not clear. There is no connection known. VP equal to VNP implies PIT in sub-exponential, that is known. PIT to lower bound, not clear, both in the VP-BNP and the matrixity. So these 3 topics seem to be very, I mean, somewhat related, but not exactly intimately correlated, right? And we want to understand one theme which solve everything. So the question is, there are a lot of problems. Should we?
Can you go to this slide?
Yeah.
So it seems like matrix rigidity is not really connected to any of them, or like you're not clear about the connection.
So people do expect that, for example, people do expect that if you have rigid matrices, you should be able to use the rigid, because rigid matrices is in some sense hard, right? So you should be able to use this to sort of blow up and come up with a polynomial which is actually hard for invariant and so on. But it's not clear how to do it. So people do expect matrix rigidity and VP-BNP, there is a connection, but it is not explicitly clear.
So any techniques for one of them should help in the other.
Yes. Yes. Because eventually we're trying to look for lower bounds, right? I mean, then there's an algebraic lower bound in some sense. So yeah, PID and it's not unclear. Yeah, so there are a lot of questions. Should we go to sleep or should we focus? And the point is that let's come up with some uniform or like one framework that solves everything. And for that, we introduce what is called the tau conjecture. Not to introduce, Schauber and Smell introduce the tau conjecture. We will study a different variant of that. But this Smell was a mathematician. He was actually a field medalist as well, and he studied some of the interesting questions. So they had this something called a tau conjecture. And what it says is that if you have a univariate polynomial computed by a size S circuit, then it can have at most poly S many integer roots. That's what they conjectured.
The polynomial is over real, no? The constants are real.
Constants.
It's
You mean the polynomial f? Yeah, the field underlying field can be rationals or rationals or reals or anything.
Yes.
Yeah, but yes. So the roots that I'm talking about is integers, right? So it says that it can have a lot of roots, but number of integer roots is poly S. That's what the conjecture says. Okay. Actually, the conjecture dates back to maybe 10-15 years back, but it was, I think, documented in the 1995 lecture. And they showed that this conjecture implies P not equal to NP over this complex, and also VP not equal to VNP. Okay. And the main idea was this polynomial. which is called the Wilkinson polynomial, which also is important in numerical algebra and so on. So let's look at x minus 1 dot x minus d. If subsmell tau conjecture is true, then it has, since it has d many roots, d many integer roots, it must have large circuit, right? That's what it's saying. I mean, if you look at the contrapositive of a subsmell, then it basically says that if it has lot of integer roots, it must have large size circuit, right? So this size of FD is large, so you can, and from there you can conclude many of the things. On the other hand, if size of FD is small, like polylog D, then actually you can show that integer factoring is easy, certainly. Okay. Then you can show that this size of FD is polylog D, then integer factoring is easy. Because if you can put x equal to 2 in some sense, and you are basically computing in some sense d factorial or something. Or x equal to d plus 1, and you got basically computing d factorial or something. And if d factorial you can compute, then sort of factorize. There is a recent result of with 2 students and 1 professor at the Marcus at MPI, where we showed actually that subsmell tau conjecture indeed implies exponential lower bound. So because previous bounds of VP, VNP and so on assumed GRH and they were just super polynomial lower bounds, we actually showed that this implies exponential lower bound very recently in the ICAL. But anyway, the point is that they were talking about integer roots, but the problem with integer roots is that this is hard because this has many number theoretic problems. Because this tau, actually this tau notation was also used in many of the papers of Ramanujan, where they talk about tau function. Sorry.
What is this tau?
Yeah, so Ramanujan had some tau function in number theory, and they got motivated by that, and then because he also was studying some number of integer roots and so on and so forth in number theoretic setting. Not in second, then they got, because Smell, the Stephen Smell, the second guy, he is a philosopher. He's a very famous mathematician.
It's an
So
arbitrarily chosen Greek character, right?
yes. Yeah, I don't know why Ramanujan started using tau, but yeah, he has tau function, tau, many things. Yeah. So the question is studying integer roots is hard. Can real roots help? Right? I think I have another 5 minutes or 10 minutes. Yeah. So the question is, can real roots help? And here's an example. I'll just quickly go over it. If you look at the Chebyshev functions, there are something called Chebyshev functions, which basically computes the cos d theta and d theta. It's actually an integral polynomial. It has, and you can show that this has d many real roots, but size is polylogarithmic. So there could be polynomials where it has a very small size circuit, but too many real roots. So subsmell tau conjecture is false when you replace integer roots by real roots. Because here is an example where there are, it is computed by small size circuit, but there are a lot of real roots. So you cannot just replace integer roots by real roots, but is there a fix? And the fix is was 12-13 years back by Pascal Coira, which is called the real tau conjecture. Now, real tau conjecture says that don't look at all sizes circuits. Let's look at a very specific kind of polynomials, which is the summation ci fi to the m. So m is a fixed. Let's say m is 10, for example. Then it is saying that sum of 10th power of polynomials, where each fi is a sparse polynomials. T many terms. It shows that then it says that the conjecture was that the number of real roots is poly KMT, polynomially bounded. So you want to write f as sum of 10th power of sparse polynomials, and then it says that then the number of real roots is polynomially bounded. Okay. Of course, m equal to 1 is true by Descartes' rule because this is sum of sparse polynomial, which is again sparse. And what was shown is that for a random sparse polynomial, when fi is a random, basically, then this conjecture is true. And what they showed, Coira shows is that if you can, if this is true for m, which is slightly non-constant, it is not a constant, slightly more than a constant, then VP not equal to VNP. It was shown. But it does not imply matrix rigidity, or it is not clear whether it implies matrix rigidity. The question is simple. Can we bring down this polynomial, this this conjecture to m equal to 2. Because that probably is the smallest case you can probably reduce, because m equal to 1 is of course true, but probably you cannot expect m equal to 1 to imply anything. Can we bring it down to m equal to 2, like sum of squares? And can you do that? If you can do some for sum of squares, then something happens. Okay. So so this is, I'll just take 5 more minutes because I'll just use this representation. So let's now look at the sum of square representation. So what is the sum of square representation? Again, m equal to 2. I want to write f as sum of squares or weight as sum of squares. Okay. And the size I define to be the number of monomials across fi's. So I have f, I am writing it as summation ci fi square, and fi has, let's say, 10 f1 has 10 monomials, f2 has 30 monomials. So you are adding up 10 plus 30 and so on. So I can have an example. So for example, 2x plus 2. I know that 2x plus 2 can be written as x plus 3 by 2 square minus this, right? So now in this particular presentation, the size is 2 plus 2, 4, because there are 2 terms and 2 terms, like 4 terms. Okay. Okay. Now there could be many presentations of f as sum of squares, right? So take the minimum sum of squares sum, like where the this summation sparsity is smallest. Is the definition clear? Because this is what the I'll just spend another probably 1 minute. So I want to write f as sum of squares. For a particular representation, I am taking number of monomials across fi's. Now, single f can be written as in many ways as sum of squares. So you look at all the sum of sparsities and then take the minimum of them. That is the measure. That is called the support sum. And it has a trivial bound, right? Because any f can be written as f plus 1 by 2 square minus f minus 1 by 2 square. And so SF is always bounded by sparsity of f plus 1 2 times, because f plus 1 has sparsity f plus 1 and f minus 1 also has sparsity f plus 1. So this is the trivial bound, right? What turns out is that there is a lower bound of square root of sparsity of f. So if you want to write f as sum of squares, if SF is the minimal size, then you can show that the SF is greater than or equal to square root of sparsity. Let me not get into the proof. It is, but what it shows is that if sparsity of f is d, then it is bounded in between square root d and d. And for a random f, it is actually d. Okay. So you want to write f as sum of squares of polynomials and understand the number of monomials across these polynomials. And for a random f, the size should be like, you should require d many monomials to write. There is no way you can do better. And yeah, quickly I'll go into this conjecture. So the conjecture is, if I have a polynomial f, then f can have order SF many real roots. The trivial bound is SF square by Descartes' rule. The conjecture is it can have order SF many real roots, and it is actually true for a random f. You want to show it for all f. So what is the SF again? Just to recall, f, you want to write it as sum of squares, and you want to understand number of monomials across fi's, and you are looking at the minimal such representation. You are saying that f can have at most order SF many real roots, and random polynomial have this. Now this is the large, this is this.
That's the minimal S or the.
S is the minimal. S of f is the minimal. S of f is defined as the minimal representation. So this is the main slide I wanted to say. So this, if you assume that SOS tau conjecture, then it implies matrix rigidity. There are explicit rigid matrices. It implies VP not equal to VNP. It also implies PIT if you have to change sum of square to sum of cubes. But sum of squares unfortunately does not work. Sum of cubes work. And of course, theorem 2, I mean, so tau conjecture implies there is an exponential lower bound. And we know that if there is an exponential lower bound, this is in quasi-polynomial. We already know that PIT is quasi-polynomial, but it does not put PIT in polynomial time. So for that, you have to work harder. But the point is, SOS tau conjecture implies all the three themes that I've been talking about. So suddenly, from real roots, you have connected all the three different problems, which is not clear whether there is an interconnection between these three problems. So the conjecture again, just to say, is that I want to write f as sum of squares, and I want to minimize it, meaning I want to minimize the number of terms across FIs. That is my SF, and the conjecture says that f can have at most order SF many roots, real roots. That's it. And for a random f, it is true. You want to show it for non-random. I mean, for all, actually, in fact, you can show for specific polynomials, you can show actually this is true. If there are candidates I have shown that if you can show this for this polynomial, particular polynomial, then also these three theorems hold. It's not like you have to show it for every polynomial. So just understand the behavior of this as a sum of squares, and you should be able to basically handle all the three questions.
Are there any implications in the other direction from any of these statements?
No, it's not clear. So for example, you are saying, for example, let's say VP not equal to VNP. Does it imply that I have a sum of squares lower bound? No, it's not clear. It is also a great question. That I mean, there should be something, but usually the reductions that I have, I mean, the way I have gone, it is one-sided usually. But it is a great, I mean, it's a very interesting question, open question, no clue.
Is there any effort to kind of make a more general statement than VP not equal to B and which would imply all these different things? In some sense.
In GCT, people have tried, but people have failed. So I don't think I mean I don't think there is a and actually this quasi polynomial comes because of this Nissen-Wigderson combinatorial design kind of stuff. This is quasi poly, so that is a basic problem in that. So I'll not talk about depth for conclusion. I'll just quickly conclude. Yeah. So the question is, I talked about two tau conjectures. One is SOS tau conjecture, one is the usual subspace tau conjecture. Subspace tau conjecture says that talks about integer roots of a size S circuit. SOS tau conjecture says you are only looking at sum of squares representation, not any size S representation. So it is much more restricted in some sense, because sum of squares is a very specific kind of representation, and but there you are looking for real roots. So can this conjecture imply PIT in P? This is one question, and so ignore the second question. The third question is very important. Like, if I have an algorithm, good algorithm, can I convert it into a good lower bound question? Right? Because the opposite one, sort of, if I have a hard instance, then I can turn it into a good algorithm. What is the opposite way of doing that? That is not clear.
Is VP equal to P imply VP not equal to VNP?
No, that is also not. No. Yeah, all these questions are so all this algebraic like VP VNP versus all the Boolean. It's not very clear what are the connection. Of course, P not equal to NP implies VP not equal to VNP or P slash poly VP, but otherwise it's not clear what is the connection. Because these are two slightly different flavored, I think, and also you have to talk about non-uniformity because of the circuit. I mean, P slash. So that is why P not equal to NP implies VP not equal to VNP is not known. What is known is P slash poly not equal to NP slash poly. The non-uniform version of P not equal to NP implies VP not equal to. Because this is a circuit notion, so you have to talk about non-uniformity. So yeah. But yeah, so that's all I wanted to say. Yeah.